Hello again. What I want to do in this video is just kind of quickly talk through Avogadro's law, the ultimate combined gas law, and then introduce the ideal gas law. Alright. So in addition to kind of looking at pressure, volume, and temperature, our early chemists, Boyle, Charles, Avogadro, they also looked at the relationship between volume and moles. And what Avogadro found was that volume and moles have a direct relationship. So in other words, if you have more moles of a gas, it takes up a larger volume. Kind of makes sense when you think about it. If you have more of something, it's going to take up more space. So let me just kind of work through one or two of these on this page. So number one, we have a 5.6 liter balloon that contains 1.2 moles of helium. We're asked how large will the balloon be with 3.40 moles of helium. So again, this is very much like how we did the combined gas law. 5.6 liters. Oh, guess what? That sounds like V1. 1.20 moles. That sounds like N1. Again, moles is N. How large will the balloon be? Oh, V2. We want to know its space with 3.40 moles. That would be N2. So, we just plug in. V1 is 5.60 liters. N1 is 1.20 moles, and that's going to equal V2 Rx over 3.40 moles. That's it for Avogadro's law. Obviously, I need to finish solving this. Maybe I shouldn't say that's it. So again, cross multiply. Let's bring up 3.4. So 3.4 times 5.6 divided by 1.2. And we get that V2 of, I have to squeeze this in there, let's look, 3 sig figs, 15.9 liters. Makes sense. We have more moles, so our V2 should go up. Maybe just one more on this page. Let's take a look at number 2. For number 2, we have a 4-liter balloon that contains 0.21 moles. Ooh, so that looks like a V1. And 0.21 moles of helium. That looks like an N1. Again, notice I'm going through the problem, and I'm identifying what variables we have and what we're solving for. How much helium must be added? Okay, when we talk about quantity, a lot of times we're talking about moles. That would be N2 in order for the balloon to be 7.12 liters. So that sounds like a V2. So there we go. Volume and moles. No pressure, no temperature to worry about because they are constant. So V1 over N1 is going to equal our V2 over N2, which is what we're trying to figure out. So this is the first case, at least one that we've done together, where N is on the bottom. So again, I would cross multiply. So I'd bring up my N2. So I wind up with N2 times 4.00 liters. Again, guys, if you have the unknown on the bottom in the denominator, first step should always be to cross multiply. And now the math, I think, makes a little bit more sense. So again, cross multiply, bring up the x, and then we can multiply 7.12 times 0.21, and then divide both sides by 4. And we get our N2 as 0.37 moles. But be careful there, because we're looking for how much helium must be added, not just how much we have at the end. So we got to subtract. We would need another 0.16 moles of helium to reach that volume. Again, the final number of moles will be 0.37, but we're looking for how much helium must be added. All right, number 3, I'm just going to kind of let you work that out on your own, but let me give a hint. We have 0.75 moles of gas initially. We have 0.75 moles of O2, and it's going to be converted to ozone. So you might need to consider a little stoichiometry there to get N2. Just a little hint. We have a V1, we have an N1, and then we want to know V2, meaning we should be able to plug in the N2, that second number of moles. And again, might need to do a little stoichiometry for that one. So get that first, then plug in. And you can check your work by looking at the answer keys we have posted. But let me kind of keep moving on to the ultimate combined gas law. So the ultimate combined gas law, I don't really think we do anything with this, but we can add Avogadro's number in there. Not Avogadro's number, Avogadro's law in there to get the ultimate combined gas law. And kind of why that's important to us is, again, early chemists did this work. They found out there's this relationship between pressure, volume, moles, and temperature that always equal out to a specific constant known as the gas constant, which we represent with the letter R. And for the units we like to use, liters, atmospheres, moles, and Kelvin, R is always 0.08206. Now we can have different values of R if our units change, but if pressure is in atmospheres, volume in liters, moles, N is in moles, temperature in Kelvin, R is always that 0.08206. And why this is useful to us is because we can kind of substitute in this ideal gas constant, R, and come up with a new formula, the ideal gas law, which is PV equals nRT. And this lets us relate all of those measurable properties of a gas, the pressure, the volume, the moles, the temperature. It lets us relate all of these together. Now again, when we do the ideal gas law, pressure has to be in atmospheres, volume must be in liters, N has to be moles, R is always 0.08206, that's a 0, and temperature has to be in Kelvin. So again, a little bit different than the combined gas law where we could have different pressure units, we could have different volume units. We have to have these specific units. So let's try some of these out. Again, I think I'm on page 9 right now. So using the ideal gas law, what is the volume? Okay, it sounds like we want to know volume. And notice, class, what I'm doing again is I'm going through and identifying all of my properties. 1 mole, so that's N. So what is the volume of 1 mole of gas at the conditions of STP? Okay, so STP, remember that's standard temperature and pressure. Remember, standard temperature is 273 Kelvin or 0 degrees Celsius. I wrote that way crazy. And standard pressure is 1 atmosphere. So like we've been handling all of our gas properties or gas law questions, we identify what we know in our formula and solve for Rx. So we're looking for volume. So standard pressure is 1 atm. We want to know volume. N is 1.00 moles. R is always 0.08206. I'm going to be a little bit lazy and leave off my units. And then my temperature, again, has to be Kelvin, 273 Kelvin. So 1 times 0.08206 times 273 divided by 1, and I get my volume of being 22.4 liters. And that's, again, kind of how we can use the ideal gas law. We do have one more question on here, and I guess I can do it. We may or may not do gas stoichiometry today, but what we kind of just discovered here is another conversion. So as long as we are at STP, and that's kind of the key there, if we are at standard temperature and pressure, 1 mole of a gas always has that volume of 22.4 liters. Always, always, always. That is going to let us convert between moles and volume. So I want to know 100 grams of oxygen. What volume would it have? So again, now we have this conversion between moles and volume. And we know if we have grams, we can go to moles. And then once we get moles, we can use this to get volume. Again, we may or may not do more of this. I'll just kind of set it up and show it. I wouldn't worry too much about this problem. I might just maybe skip ahead till I'm working the next page. So 1 mole of O2, we could use our molar mass of oxygen. And then again, as long as we are working under those conditions of STP, 1 mole of any gas has that volume of 22.4 liters. So I could set up my molar conversions that way. 100 divided by 32 times 22.4. My sig figs would come back to here. And I would have that volume of 70.00 liters. Again, as I look at this, I honestly wouldn't stress too much about this kind of mole conversion I did here. We may or may not get to gas stoichiometry. We haven't decided yet. But if we do, as long as we are at STP, remember 1 mole of any gas has that volume of 22.4 liters. So it's just kind of why the ideal gas law is one example of why the ideal gas law might be useful. I wouldn't stress too much about this right now. If you're like, what the heck? Again, don't worry, just focus on being able to use the ideal gas law, like on number 1. So number 1, if I have 4 moles in of a gas at a pressure of 5.6 atmospheres, P, volume of 12, what is the temperature? Oh, ideal gas law, N, P, V, and T. So let's plug in pressure is 5.6 atmospheres. That is the correct unit to use. Volume is 12 liters, also in the correct unit. Moles is 4.0. R we know is always 0.08206. And we want to find our temperature, that is our X. So that's how everything would be plugged in. So 5.6 times 12 divided by 4, and then divided again by 0.08206. And I get my temperature as, oh, this is really annoying because I hate the sig figs on this. I get something like 204.728 Kelvin on my calculator. But if I look at sig figs, I think I should only have 2. Again, I don't like this. I'll just tell you the final answer should be 2.0 times 10 to the second Kelvin. Again, you would round it to 200. That only has 1 sig fig, so we change it to scientific notation. Again, real annoying. But I'm going to kind of wrap it up there. That's what the rest of this page is like. Again, you have access to just the answers, so check your work. And also make sure that your units are all correct. Again, pressure in atmosphere, volume in liter, moles in moles, temperature in Kelvin. So just watch that as you go through these.